Good morning, good afternoon. How are you today? We are back again with another series for Visual BACnet troubleshooting. Now this time, a little bit more exciting, we are going to go through this live and troubleshoot a couple files that some of our very lucky Visual BACnet users have provided us. These are we've taken a look at these files a little bit ahead of time, as they're a little bit scary. There's a lot of interesting things that we found in this file, and I really hope that going through this session we can shed some light on it and make troubleshooting on some of these problems will make it a lot easier going forward. So I've got Ping here with me as well. So we've got a bit of networking expertise, a little bit of BACnet expertise, and we'll go forward and take a look at this file. So the first one we're going to start with here today is a corporate building. Now this particular corporate building, it's quite a big file. It was taken, the capture was taken for about an hour and a half, and it's got 2.5 million packets inside of it. Why that's relevant is if you were to look at 2.5 million packets inside of Wireshark, that's 2.5 million lines of data. That would be very difficult and lengthy to deal with. In here, put it in here, we've got a poor network health score, 23%, and just looking at the top summary, 8 failed checks and 4 are in warning. So as always, as we go through this information, we want to take a quick look at various things. You can see the traffic rate here. It's hovering on average pretty high, about 750 packets per second as a rate on the entire file, but it's hopping up and down quite severely. So there's obviously some fun in this file. So we're going to dive in a little bit. Normally in these files, we say start at the very top on the critical checks and work your way down the list. Well, in this particular case, there is just a couple unresponsive devices and 1 rejected network. So those, although they're critical, we're going to take a look a little bit deeper down into this score check section, where there's an awful lot more red in it and some more information. We'll come back to the broadcast traffic. In this particular file is very high at 32 packets per second. On average, a well-running BACnet site is about 10 packets per second. So it's running 3 times higher than it should be, but we'll come back to that. When we were diving into this file a little bit more, one of the two key things popped out at us, but one was this global whois router. This is something that should not trigger in a file very often, if at all. And you can see here this 10 or over 1,000 sources of global whois router. So when we click on that,
Ryan, because the file's so big, go to the score at the top. It's just a little faster in this case.
I'm a little bit locked up here.
Yep. So just warning everyone, this, as Ryan said, it's a massive file, 2.5 million packets. Just so you know, we brought it in yesterday into Wireshark just to compare, and a single filter in Wireshark takes about 3 minutes, 2 minutes to run, just a single filter. So if you're going to bring that in, just be aware of that.
So Ping, let's go through this one. So under here, under the global whois router, there are all of these devices that are requesting the global whois router. So they're sending out an overall broadcast, and they're looking for all the routers on the network. All of these devices are doing the same thing.
Yeah, so again, a little background on this. So a whois router is a simple message that's sent out when a device wants to reach another device on a different network. It has to figure out what network it's on, and it just says, who's the router to network 123, whatever. And a global whois router would be saying, hey, every router out there, please tell me which network you are the router to. So if you're in a small system and you have a couple routers, BACnet routers we're talking about here, BACnet routers, it's not a big deal to do a global whois. In this case, we should have shown you earlier, but in the summary, I took a quick peek and it looked like there was over 50 networks, BACnet networks. So there's at least 50 routers here. So you're shouting out saying, hey, every router out there, BACnet router, please tell me that you're there and what network you're the router to. So that's a global whois router. Yeah. Ryan, you want to keep going?
Yeah, absolutely. So in here, we can see that each one of these devices has sent out 4 requests for a global whois router. If you take an average of that out of an hour and a half, they're sending out the request approximately every 20 minutes. But all of these devices are doing the same thing. So let's dig in a little bit deeper and see what that actually means. You can click on any one of these rows, and it opens up another menu down here at the bottom. So
Ryan,
these
can you
are
zoom in a tiny bit? Can you zoom in a little bit just to help everyone follow? Yeah, that's good. That's great.
perfect. So in here, the packets for this source, this is the one that's sending out the information. We can actually click on the row within that expanded menu, and we can go see what it's trying to do. So we can see that each one of these, and this is where we get the time, right? Every time at, looks like 4:43, and then again at 5:13, and then again at, it's very specific. So whatever's happening on this source device, it's doing it at the exact same interval. That's why
And
we
by the
get.
way, what this tells me is that this is not triggered by a human, right? So it's not an operator going out there and say, hey, I'm doing a discovery. I want to find out everything. I'm trying to create a database of some sort. This is programmed in. You can tell it's exactly every 30 minutes. So clearly it's in the programming, these devices every 30 minutes. We can look other ones, but you can see that this is every 30 minutes. So right away it tells you it's not a human operation, right? So sometimes global whois or global whois router, it's used for discovery that we as humans operators want to use. In this case, it's part of the program. Ryan, can you also expand what we call the BVLC, the BACnet Virtual Link Control? So
Yes. Go ahead, King. This is a little bit about BVMDs.
yeah, I was just going to say here, one of the interesting note here is you see under BVLC, BACnet Virtual Link Control, the function it says for the NPDU. So for the NPDU means that this packet was sent through a BBMD. Where you're capturing right now, this customer, this user of ours, captured it at the output of a BBMD. So that's fairly important to note, and that also, if we're on here, you can see the IP address source of the packet at the bottom does not match the IP address at the table at the top. So at the top right now, Ryan is clicking on this 10.200.100.116, but the packet itself. So if you were in Wireshark and you filter by source IP address, the source IP address will be 10.200.254.100. And what this shows is that the .100, 254.100, combined with the fact that the BVLC shows that it's a 40 MPDU, the BBMD address is 10.200.254.100. But the message itself originated from 10.200.100.116, which you can see both at the top in the table and on the bottom at the IP address, just 2 rows down from that point there. So again, this is all information that are available in the packets. You could try to do this in Wireshark, it's just a lot of work. But here in Visual BACnet, that these devices are going through BBMD and requesting a global whois router. So it's shouting out, every router out there, please tell me you are there and which router which network you're the router to.
So this probably should be done this exercise should be done maybe once a day or something a little bit less, because it's unlikely that your router is going to change or come online and offline. And it's very unlikely that you're going to keep adding routers to your network. It's kind of like Google Maps creating a bunch of routes. It's already there, and they just choose the one based on your location. So unless something happens and the route needs to change, or we add a brand new road, which is a new route, which doesn't happen as often. So Chris, if you're out there watching the webinar, this is your file. One of the things to take a look at is here's all your source devices on what's happening in the network. and you need to figure out why it's doing this particular exercise.
Yep, and as Ryan showed earlier, there are over 4,000 packets that are shouting out, and the responses. Remember, the responses shout back. They are also broadcast. We can show you that in a moment. But as Ryan said, these should not be necessary. It could be a couple things. One, it could be just that discovery needs to be turned off or turned down, or it could be a caching problem. I don't know enough about and what product this is, but it could be that the caching table may be limited, and therefore every message that goes out there, it needs to ask. So if you can clean that up, you'll get a much higher performance in.
Absolutely, a much higher performance. There's all these devices that are asking every 20 minutes, right? I mean, the packets go up. There's another way to look at this as well, and that is based on the service choice.
Yep. Yeah, massive file, so give it a moment. We have a fairly optimized database in the back end, but even then, with 2.5 million packets, it does take a while to crunch through it. So while we wait here, whois router the response will be an IM router 2 or IM router, and both messages typically will be broadcasted. And now you're doing a whois router to all routers global, so this is not directed. So you're not saying who is a router to network 123, and then if you did a directed whois router, again, a whois router to network 123, only the router to network 123 will respond. But in this case, every router will respond with a broadcast message. And again, the other thing to keep in mind here is that all OS-based computing have a limited processing power. So let's take, for example, a Raspberry Pi. If we load a BACnet stack on Raspberry Pi, it could probably handle about 1,000 packets a minute without choking too much. So very often when we say the network is slow, it's not necessarily the network itself that's slow, it's that the devices that are networked are getting so many messages that it cannot process all the messages. And that's why it's so very, very important to turn down as much broadcast as possible to leave room for processing the messages that are meant for that device.
Yeah, and you can imagine a BACnet router. Some of the devices today run a 1 or a 2 gigahertz processor inside of it as a router, not a big deal. But that poor little MSTP device, it's a zone level controller, might only have a 100 or 200 megahertz processor, if that. So there's no way it can handle all that broadcast data.
Let's move on, Ryan. There's a lot of load on the machine yet. Let's move on. Maybe go back to summary, or let me see if I can bring it up. Sorry,
I'm getting all choked out here.
Yeah. Okay, I am here. You want to stick with the corporate building, Brian?
Let's do one more thing in the corporate building.
Sure.
Because there's another thing that we found that we wanted to go through. So under the corporate building, again on the right-hand side, there was this unconfirmed COV traffic. Now, typically unconfirmed COV traffic is very, very minimal at best, but inside of this file, it is showing us at 8 packets per second of unconfirmed COV traffic. That is really, really high. Normally, we almost see nothing inside of this. And this is going to tell us what is actually happening. So this is showing us all of the device, the object type, and the object instance of what the device is and what it's sending. So here's an example of this device, 707105, an analog input 6, sent 47,000 packets inside of an hour and a half. You can imagine that that is insane. Now, how is it possible that an analog input is sending that much data all the time? Well, once we dig into the packet and click on that row, what we see is the source is sending it to this destination and it's sending the present value. But the present value is 1.008, 1.219, 0.997. Most likely the send interval on the change of value is much too tight and it's sending this way too often. So you can see every second, and it's even higher than that because we only read the value down to the second. So when we're down to the microsecond, it's sending data more often than we're even seeing here. So the same input value is triggering and sending data packets multiple times per second. This is an easy fix. You simply go into the point and you change the COV increment. However, or you change it to polling, or you change it to a something a little bit different than what it is. But that's what's causing all of this broadcast issues here, because we're asking, or the COV write issues. So we're asking for the data much too often.
Ryan, do you mind clicking on one of these packets? I'm kind of curious a little bit. Okay, so here's the good news. The good news is that these messages are unicasted. But the bad news, again, is that there are 40,000 packets, whatever Ryan just said. And both machines here, if you think of it from a machine point of view, this machine 10.200.20.5 has to collect the data, create the message, and send it out. And then the other device, the recipient 10.200.254.200, now has to unpack the message, process the message, and then display it or do something with it. So again, the network itself might have lots of room. It might be able to run a gig, but your machines here are consuming a tremendous amount of memory and IO cycles and CPU cycles to create, process this data.
And a lot of this may not be relevant, but here you can see it's actually asking for more than just one piece of data. It's asking for a list of values. So it's asking for who the vendor is. It's asking if it's out of service or not. It's asking for the present value, the reliability, the status flags. So it's asking for a lot of information here within that packet as well.
Yeah, so again, every field has to be processed, right, in the software world at this point.
Good news is for Chris, if you're out there, is this one line, if you can reduce it from almost 47,000 packets down to something a little bit more normal, like the 3,500, you're going to be in a lot better position. But I would also check on these other ones as well, because that's a little bit high.
Yeah. Let's just click on one of the other ones, Ryan. I'm curious also who the recipient is. So in this case, again, this takes a little bit more understanding of the system, but you can see here is a different source, so different device sending it out, but the recipient is the same machine, 10.200.254.200, right? So that machine, again, it already has to process 40,000 packets from this other one, and it still has to process packets from others. So, I mean, unless you're running some massive machine, you're taxing its, again, memory, IO, and CPU.
Perfect. So now that we know what the actual device is, we know what the BACnet device is, we know what the analog input is, and we know what the value is, then it's going to be very easy to go to your front end software and do some changes, right?
Right. I just want to let you know that we did get a comment from the audience that unfortunately we do see by mistake COV set to 0. Unfortunately, that can cause problems like this.
Okay.
Yeah. Thank you, whoever forwarded that.
Perfect.
And the same person also sent a comment. Usually we get a complaint from the customer, why are my graphics so slow? And there it is. That's exactly what it is. Your
Because
refresh rate is very high, but the machine is not able to keep up with the actual drawing of the graphics. Thank you for
the
that.
Elmo one, there's also, now that you mentioned that, let's take a poke at the longest response time here.
Yeah.
Because this is where it gets quite fun. So the longest response time, we have a list right here on the top. That's 6 seconds. So when you ask for data, it took 6 seconds to come back to you. And this is machine to machine. This is not me asking my wife to go do something and she's ignoring me and then I get a question. This is machine to machine. And that data should come back sub-second, if not in milliseconds of response times.
That's right.
So
If you look at a network that's MSTP based, having a response time in the 1 second, half a second, even though it might be a little high, it's common. But when we look at an IP network, when something takes 6 seconds, it is not normal at all. I mean, we can through the internet, you can get data from the other side of the world and back within a second, a few hundred milliseconds. So what this says is it's unlikely the problem to be in the network again, right? So it's not a switch that's not keeping up. It's not that your bandwidth is too small. Increasing the performance of your router or your switch will actually probably make the things worse here. It is very likely that either the requesting device or responding device, again at the OS layer, at the software layer, it's taxed so much that it's not able to keep up, and therefore it slows down.
well, let's dig into that. So here we've got a requesting device. This is the 10.200.5160 or device 9998. It is actually asking information from this device, the 254.200. Now, if you recall in the last check that we were doing, that all of that data was being asked by that 254.200 device, which means it's already processing a ton of packets. It's doing a lot of work. And now we're asking it again for more information.
Oh,
And what we're asking it, go ahead, Ping.
no, I just realized the response is abort. So it's not
Yeah,
even responding. It's not like 6 seconds later, even though it's slow, it got there, right? It actually didn't even respond. It responded with sorry, I give up.
it gave up. It absolutely gave up.
Yeah.
So it just says, okay, it's been here too long. There's no data for you. We're out. So that tells you a lot that whatever device is 254.200 is completely overloaded and things need to be toned down a little bit.
Nice.
But again, here the response time is very consistent all the way through. We've got a lot of things at 600, but it looks like multiple devices are being asked, and that same device at the end is constant in the problem. So between the original problem of the global whois router, between the analog input being requested too much, and this problem, this 10.200.254.200 is the center of all three of those checks.
Yeah. Now keep in mind the problem could be that the problem is not with this device itself, right? It's just that the device is the one that's exhibiting the symptoms, but the problem is likely, in this case, looking at it, it's likely that the whole system is set up with too many global whois router. It's the COV is going to that machine and it's much too high rate, and everything is asking for information from that machine. So again, not knowing what the system is, if we cleaned up the global whois router and we turned down the COV, I think we would probably see a significant drop in requests, and which would significantly improve the performance of the overall system, but definitely of the 254.200.
I would agree. So Chris, will be looking forward to your updates on this as you work through the file. And for now, let's go to our other file that we have. So is there anything else you want to cover in this one?
Let me just share very quickly my screen. Natalie, if you could switch that over. I was able to bring up what we call the BACnet browser. It's not a big deal, but let me see here. Here. Okay. So here's the the BACnet browser of the same file we just looked at. And if we click on service choice, I just wanted to show here the who is router to network. There are 3,200 packets out of that 2.5 million, so it's not too bad. But you see this I am router to network. So if we click on that, these are all the responses to the who is router, and it's just capped, and it's all across the whole spectrum and time, right? It's constantly just sending messages, and this is all broadcast packets, and so again, just putting a lot of pressure on the entire network, and more importantly on all the devices that are connected.
Was that 160,000 packets in here?
That we had?
Yeah, so that would be almost 5% of the packets in this file is just this.
145,000. That's right.
Yeah, 5% of the file.
That's right.
That's pretty heavy.
Pretty heavy, yeah. Now, if we could switch back to Ryan's desktop, please. Thank you. Keeping her busy. All right, Ryan, you want to look at a different file, is that right?
This is our second file. This is from a hospital. This one has come to us with not as many problems, but a few. The overall health score in this file is 29%. And again, it was a good hour and a half capture, just about an hour and a half. So that's a good amount of data. There's not 2.5 million packets, there's 125,000. So it's going to be a little bit more easier on the network to troubleshoot. But this is pulling data from a network size of about 1,500 BACnet devices. So a pretty good sized network. As we can see going through this, there is, starting with the critical checks again, you see a whole bunch of unresponsive routers. But one thing that caught our eye right off the top is not necessarily unresponsive routers and devices, but I noticed this missing acknowledgments, which is almost 74% of the entire file is missing acknowledgments. What that tells us right away is that we were asking for lots of data and never got a response from what we wanted. So this is a spot that we would start with right away, because as soon as we go and figure this problem out, I'm pretty sure that the unresponsive routers, devices will come back, the broadcast traffic will drop, and along with a few, probably the longest response time as well. But we'll dig into that and we'll see what's going on.
Yeah, so a couple of notes here. On the far right side, far right column is missing ACKs. Right now it shows 100%. So every request that goes out, whether it's complex or simple, it does not respond. If we wanted to go back, and we won't, but if we went back to the other file that we were looking at, corporate building one, we would see some missing ACKs, but it's not 100%. So that typically indicates that the device is just too busy to process everything. But in this case, because it's 100%, it likely means that the device went offline. The programming is slightly incorrect, like it's looking for something that's not there. A router went offline. So basically, the communication is just flat out not working.
So one of the things you're going to do when you troubleshoot is figure out what it's asking for and then decide if that's supposed to be there or not. This particular one is the source destination is device 51,100. So it's the one that's asking for the information, and then it's trying to get the information from this guy here. We'll dig into the packet to see what that is. So what it's asking for is read property information. And it's asking for a confirm request. Confirm request means when you're doing a read, it's automatically confirmed because you're reading data back. It's asking for a multi-state output or an MO object, and it's asking for the present value. But what's happening is it's not getting that response. And then can we tell? So the destination, so the source, so it's going between the two networks. So it's asking from the The source network address is where that 51,100 device is sitting on, and it's asking for the information from the 50,000 network.
A couple of tricks I wanted to show everyone here. So Ryan, if you hover over that first table there above, when you hover, you can see it will pop up something. So on the very first row, it shows you the source, but doesn't show you destination. Just hover down to the next row, please, Ryan. And I'll explain what you see there. Source again, keep going down. Destination unknown, keep going. One more. There it goes. So this one, it popped up and it showed you both the source and the destination. All it is this is correlating data that we're having in other places in Visual BACnet. When Visual BACnet is able to find the vendor name, the BACnet ID, the source address, and sometimes that information is only available in frames like IAM or so on and so forth. Whereas in sometimes there are frames that all it has is a BACnet ID, or all it has is the BACnet address, the source address, destination address. So what this says is that this packet here, or this machine here, the destination device, we did receive like an IAM from it. So that's an interesting thing. Whereas in the very first row, you could see the source, but you didn't see the destination information, which is very, very consistent with what we're seeing here, because we weren't able to gather additional information on the destination machine. Just little tricks in the Visual BACnet.
Perfect. So under here, under all those files, we've got, we're looking for a lot of information that's not giving us a response. So this one here was the MO object. This one here is, again, looking for another multi-state output. This one here is looking for an analog output. So the common theme here is you're not getting any data back. So the source would be, first of all, check this device right here, 51,100, and determine is it asking for the right information? And then if it is, then we can turn our attention to the device that should be giving it back to you.
Yep.
So coming out of that, if that's true, then we should start looking at the routers, because odds are the information trying to go from one part of the network to the other is going to continue from here. So now when you're looking for different BACnet routers, you've got this destination network is sending a whole bunch of information. It sent 343 packets and none of it got an answer. So is the device online? Is it even supposed to go that way?
Yeah.
And here, you had something, Ping?
No, keep going.
Here, you've got a querying device that sent packets. So we know exactly which device it is by MAC address. And then we can go see what it's actually asking for.
Yeah. So this is, it's kind of neat that we had these two files to compare. The corporate building file that we were looking at earlier, we had excessive amount of global whois router to network, whereas in this one is what we call a targeted whois router to network. So this message is being sent by this querying device saying who is the router to network 20528, and it's not getting a response. It's not getting an IAM router to 20528. So that's a normal frame, a good frame, but for some reason it's not responding.
Correct. So a lot of whois router to network here as well. And this is different than the global whois router, but this is saying I'm trying to, this device is trying to send data to this network and I don't know where it is.
Yeah, and one thing you can point out, Ryan, if you scroll up a little bit, that first table shows you the destination networks that are being requested. So Ryan clicked on 20,528, and when he clicked on that, there was only one device that was asking for this network. Okay, so the good news there is that it's likely programming on this device, as opposed to seeing 50 querying devices looking for this network. I don't know anything about the system, so I can't say for sure, but if there were more than one device looking for this network 20,528, it's likely that the router went down. But in this case, because only one device is looking for this network, it could be that this device has incorrect programming. We did a copy and paste, we moved the database around, whatever it is, we changed the router, we never updated it. Let's click on a couple more just to see, just to compare. That you see that one? Yeah, that one's
more crate devices. This, yeah. Keep in mind, during construction, you may see a lot of this where you would have programming in the device before the other zone devices are up and running. But look at the impact it does have on the network, even during construction.
Yeah.
So as being stated in here, there's 4 querying devices trying to get to this network.
Yeah, and here's sending it every minute.
Yeah, every minute it's taking a look. So it's trying to get to a different source port. And this one through here, this is the original broadcast, so it's still within the same BACnet segment.
Mm-hmm.
And again, router to network. And all of these are very similar, coming from the same network. The second that the BVLC function goes to forwarded MPDU, then we know we're crossing BBMDs.
Correct.
So a little bit of work on there to figure out, looks like you've got some work to do, Phil, to figure out what's happening on this network and targeting these querying devices on the source. So it looks like your router and your missing acknowledgments are going to be related.
Yep.
Now, if you pop back into this file, there's another piece that we wanted to look at, and that was, well, there's 3 things I want to look at actually. One is the BACnet broadcast traffic. This one here is this device here, the broadcasting device. It's sending an awful lot of information in this file. Remember, the file itself was only 125,000 packets, so almost 15,000 of those are broadcast device. We're trying to figure out what it's actually sending. Who isn't really a big deal. The unconfirmed private transfer, this is more of a proprietary information. So it's sending these fairly consistently. Let's see what else is here on the network. So a bit of a combination to both. I don't recall ping the unconfirmed private transfer probably shouldn't be a broadcasted device. I think it should be a direct unit.
Yeah, I'm a little surprised there, although I don't know enough about the private transfers to comment intelligently, but that'd be something to look into.
This is probably sending up like trend log data or something else, but it should be sent to one direction.
Yep.
So you might want to check your data exchange settings and see what's going on there. And you can tone that down a little bit. The other one that was interesting to us was this alarm. So what the alarms do is we trigger the alarms if they go from normal to off normal within the length of time within this capture. So what we're seeing here is there's an event enrollment alarm that has gone off, and it's gone. So here's the event enrollment device or object type, and then it has the object instance is 9. So what it's done is this is triggered 12 times over the past hour and a half file. So that's pretty consistent. If your alarm's triggering that much, I mean, a lot of times the alarm should trigger almost never, if anything, every couple of days, depending what the problem is. But this is a consistent problem within the hour. So from here, obviously, it's hitting the high limit a lot and then coming back. So it keeps flipping back and forth, back and forth. Now it looks like this is hitting 4
times, it looks like.
Yeah, it's pretty consistent, isn't it?
Mm-hmm. Yep.
It looks like about every
4 times to 4 different destination, or can you expand the Ethernet header? So no, it's broadcasted. So I don't know why it sends it 4 times. I'm not sure.
Device 63.
Maybe there's different data in it. Expand the APDU, Ryan. Yeah, so it looks like it's sending out a bunch of stuff. I'm not too sure. I'm not too sure, but that'll be something interesting to look at.
Seems like the same piece of data. So this is looks like a filter alarm based on pressure. So something here is probably alarm. The alarm value is a little tight, and it could just be reduced. Or maybe it needs a lockout, something similar to that. But it is I mean, obviously, as we know in BACnet systems, I mean, if the alarms aren't tuned correctly, then you're going to have quite a bit of data. And as we all know very, very well, if there's too many alarms, they get ignored. So this is a really good indication of seeing the same alarm triggering back and forth. And it's a way, the way we identify it means the alarm is triggering on and off way too much. Normally in most files, we never see this trigger.
Yeah.
And then last but not least, we have a longest response time. Now, oddly enough, between this file and the last one, they're both at 6 seconds, but that's purely a coincidence.
Yeah.
But where it helps you here is this requesting device is asking data from this device over here, and it's taking 6 seconds to respond. As a quick note, inside of all BMS programming, if you set a device or if you set a data request from one device to another, we can always time it. So if you suspect your system is slow, set a start and source and end destination, and we can simply time it and see how fast it's taken for data to get through your network. Yeah. I know what customers say, my graphics are slow. I mean, that is a very, very, very vague problem, and it takes a while to go search, but this is a good way to see it. So what we're asking for here is from those two devices, we're actually asking for some information from the device object specifically, and we're asking for all of this information. So it's a read property multiple that's trying to send all this information back. And it's taking 6 seconds to collect that data, which is way too long. But we know what device it is, we know what the two controllers are. So the job you're going to have now is to determine in a BACnet network on what's in between source and destination device.
Yeah, and a couple of notes here, 3 notes. One is the response actually it's successful, right? So you can see it sends out a read property multiple and actual response with the acknowledgement for the read property multiple. So it is actually working. So the data is getting there. It's just getting there a little late. Observation number 1. Observation number 2 is that at least for the top 10, it's all the same requesting device. So you know what's happening there. Again, I don't know the system, I can't comment. And observation number 3 is that unlike the first file where we looked at and there were a lot of messages that took 6 seconds and above, in this one there's one pair of messages, one thread that took 6.3 seconds, and then it drops immediately down to 1.2. So the good news here is that it's not a problem across the entire system, right? Something happened between these two devices at that time that took 6.3 seconds. It could be that responding device, someone logged in and did a big, graphics grab, and it just chugged along for a while, and the CPU was locked on that, and then it went back to normal. So the good news there is that it could just be an anomaly. It could be just that one device, or it could be just on the cusp, and therefore once in the blue moon, you get a very, very long processing. Unlike the first file we looked at where we had a consistent over 6 seconds, and in fact, they aborted that one.
Perfect. So there you go. We've got some work to do and getting through it. Odds are some of those routers may be a problem in here. They probably are a problem. They could be causing some of this delay, but we've kind of given you an order to look at. Definitely look at those acknowledgments in as well as those unresponsive routers, and this network is going to be golden very, very quickly.
Yep. One quick note from the audience, it was good advice here. When we are troubleshooting, especially look at a system that's a lot bigger, it does help sometimes to look from different point of views. So someone in the audience suggested, coming back to that corporate building file example, if we pulled a file from that 10.200, 254, 200, it might give a different perspective of what's happening. It's a very, very good point there. When you're troubleshooting something, when you're evaluating the health of a system, it does help to take captures from different points. If you might have MSTPs, it'll grab it from the BBMD. If you can do mirror ports, a great way to do it also. Yeah, thank you for that.
Always helps out both sides of the conversation.
Yes.
Alrighty, great. Please ask away on any questions. That's all we have for these two files. I hope you found them very informative. As always, we at Optical Networks are here to help. If you're stuck or struggling with a file, we are happy to help. If you're stuck in capturing and trying to get the data, we are also here to help. This is what we do. We live and breathe this. So anything we can do to help you, that's what we're all about. That's why we created this. BACnet's great, not without its problems like anything else. And we just want all your sites to be perfect.
Quick question from the audience. Can the BACnet browser in Visual BACnet show messages between two devices for write to a specific instance of a specific object? It is not currently possible. Thank you for the question. We'll take that as a feature request. And if you do need help, let us know. We might be able to script something up custom for you, but it is not currently possible.
Yeah, not at the moment.
Yeah.
However, out of curiosity, we can look at, where was that? So in the other file with the unconfirmed traffic, so even at this one here, this is showing us the object instance. So we can, I believe you can do a search inside of this to look at the object instance. So inside of this, if the data is already being sent, then there's a portion of it that we can narrow down.
Yes, good point. Actually, you can do the same. So this example, this question was about write properties. So let's see if there's any write here, Ryan. Let's go to summary, write property. If there are not, we'll look at read property. But I believe Ryan's right. There is a way to do it because so there's no write in this file. Let's see if there's some reads. I believe there are.
I'm not sure if we can get that out of the type.
You can, but it's digging in a little bit, right? If you want to look at a certain object, you have to open up the frame and look at that. It's a little clunky there. It'll be on the service choice, I think, Brian.
Yeah, I think you're right.
So there's no write property you can see here, but there's some read property. So let's go back to summary and look at the read property. You might be able to get, again, if there are write properties in your system, you might be able to use that write property check to pinpoint that specific object you want. But for example, here we'll use a read property. So here it does pull out the object instance. If you know what instance you're looking for, you could sort or search for it. It might give you the information you want, and it will also give you, I think it'll give you both the request and acknowledgement. Can you click on one of them, Ryan? I just want to make sure that I'm not providing incorrect information here. Right, so there's no response time on this one. This one might be the one with a lot of missing acknowledgements. But I think you might be both frames. Yeah, wonderful.
Perfect. So there is a method of doing some of this.
Yeah. Hopefully this helped.
Yeah, echoing what Ping started to say. Hopefully this helps. We do these periodically every couple months or every 6 months. So if you're stuck, get a file ready and we'll help troubleshoot it. Till next time.
Thank you. Stay home, stay safe.